So this involute profile geometry of the teeth gives rise to what we call fundamental property of gear sets, which basically says that if your input gear rotates, so let me say if input gear rotates at constant speed, then the output gear will also rotate at constant speed if the teeth profile is involute. So this is key. So the teeth profile has to be involute, otherwise you will not have the fundamental property of gear sets. Now, another consequence of the teeth profile being involute is that the two gears can be thought of as two cylinders or two discs or two wheels rolling on top of each other. Okay, now of course there is no fixed circle for a gear, because if you look at a gear, you have basically a teeth, okay, and then this could be the point where the teeth of the other gear is in contact, right? This is where it is in contact, and the contact point could be changing, but for all effective purposes, because the tooth profile is involute, we can consider the two gears to be rolling on top of each other, and the radius for these gears, or should I call circles actually rolling on top of each other, are called pitch radius, and these circles are called pitch circle. They're called pitch circle. Okay, so think of every gear reduced to a circle or a disc or a wheel having radius of pitch radius. Okay, so you have, let's say, radius r1 here, radius r2 over here. Now once we idealize gears as two circles rolling on top of each other, then the analysis becomes very, very simple. Okay, so analysis would proceed along the similar lines as we did for the pulleys. We have the contact point, and assuming there is no slipping, which should not be happening, then the contact point has the same velocity. So velocity of the contact point from the perspective of the gear 1, let's say this is rotating with angular velocity omega 1, this would be rotating with omega 2. Then from the perspective of the gear 1, we have Vc equal to r1 times omega 1. From the perspective of gear 2, Vc would be equal to r2 times omega 2, and the two have to be same, so this should be equal to this, and that means omega 2 divided by omega 1 is equal to r1 over r2. Okay, so this is similar to what we obtained for pulleys as well. The only difference is that the direction of rotation would be different for gears. For the pulleys it would be same. So in this case, if let's say r1 is less than r2, so if r1 is less than r2, which seems to be the case for this particular picture, then omega 2 would be less than omega 1, right? Which means the larger gear would be rotating at slower speed. Okay, now it turns out that for the gears, actually we really don't talk about the radius or the pitch radius in this case. Okay, what we know about the gears is, and this is another important point, is that the gears that mesh, and when we say gears that mesh, the keyword is the mesh properly. Gears that mesh properly should have same teeth density. Same teeth density. Now teeth density is measured by a parameter called diametral pitch. Okay, diametral pitch. So diametral pitch is defined as number of teeth on gear divided by its pitch diameter. Okay, so N over D, that's how it is defined as. And there's another parameter called module, sometimes written as M, which is defined as 1 over diametral pitch. So let me call this P. Okay, 1 over diametral pitch, so that would be D over N. So just the units would change, but the teeth density should be same for the gears that mesh properly. So the gears that we'll supply to you in the Snappy XO kit will have the same diametral pitch. Okay, and that decides basically what the teeth density would be. So if we know that, then we know that N is proportional to D, right? For the two gears that are supposed to mesh properly, then N is proportional to D, and that means it's also proportional to the pitch radius. Okay, so that means that in our previous relationship, which is this one, omega 2 over omega 1 being r1 over r2, this can be written as, so n, let me write this, n over d is equal to the pitch. Okay, so pitch is same, so that means that n1 over d1, which is same as n1 over 2r1, should be equal to n2 over d2, which is equal to n2 over 2r2, right? So 2 cancels, we get n1 over r1 is equal to n2 over r2, or in other words, n1 over n2 is same as r1 over r2. Okay, and that makes sense because this essentially is saying that n is proportional to the radius or the diameter, right? So this would be equal to n1 over n2. A number of teeth can be easily counted for the gears, so this is a much more useful relationship. So omega 2 over omega 1 is equal to n1 over n2. So if you know the ratio of the teeth between the two gears, then you can find out what the ratio of the angular speed. Okay, so that tells you that if you want to increase the speed, then you need to go from larger gear to the smaller gear. On the other hand, if you want to decrease the speed, you need to go from a smaller gear to larger gear. So clearly there is a speed reduction or increase depending on what you're trying to achieve. Now, what about the torque or the forces? So let's look at that as well. So let me draw my gears again. So I have my smaller gear, which is the pinion, and then I have my larger gear. Okay, and these are the pivot points about which they are rotating, and let me just choose the same direction of rotation. So that's omega 1, this is omega 2, this is radius r1, that's radius r2. Let's say the number of teeth on this is n1, number of teeth on this is n2. Okay, so let's draw a free body diagram of each of these separately. So let's say for the pinion, this is point, let's say A, this is point B. So I have reaction AX and AY, and then clearly this is going to be, the gear 1 is going to be pushing gear 2 in this direction. That means from Newton's third law, the force on this would be F that way in the tangential direction. And for the bigger gear, we'll have F pointing that way, and for B, we'll have reaction over here. And of course, we also have the torque applied. So let's say this is T0. Now let me call it T1, okay, because this is 1. So this is T1, that's radius R1. And then I have my torque on this, let's say T2, okay, that's the opposing torque coming from some sort of load, okay. Now I can do my equilibrium analysis on the gear 1, so sigma MA equal to 0, and that would be F times R1 minus T1 equal to 0, so I get F equal to T1 over R1, and for this, sigma MB equal to 0, and I have F times R2, that's positive, minus T2 equal to 0. So F from this comes out to T2 over R2. And of course, both of these forces are same. So I get T1 over R1 equal to T2 over R2, or T2 over T1 is equal to R2 divided by R1. Okay, so that's what we get. So output torque divided by the input torque is equal to the radius of the second gear divided by R1. So in this case, since this is more than 1, so we are definitely gaining on the torque side, right? So we lost on the speed side, but we're gaining on the torque side. So something like this would be useful if, let's say, your robot or machine had a larger torque requirement, and you were given a motor of a certain speed and a certain torque, but you needed more torque. In that case, you could use a gearing system going from a smaller gear to the larger gear, and then your output, which could be the wheels of your robot or something else connected to the load, so that you could gain on the torque. Okay, so we get that. Now we have omega 2 over omega 1 equal to R1 over R2. So what I want to do is I want to multiply these two and see what we get. So T2 divided by T1 times omega 2 divided by omega 1 is equal to R2 divided by R1 times R1 divided by R2, and these cancel and we get 1. So we get T2 omega 2 equal to T1 omega 1, which is nothing but the power input equal to power output, which is something that we expected, right? Now, in reality, of course, there will not be 100% conversion of the power from the input to the output, but the gears are typically very efficient, something like 80 to 90%. So if you are supplying, let's say, 1 watt of power on the input side, you will get at least 0.8 to 0.9 watt of the power on the output side. So the analysis of the gears is fairly straightforward to perform. Now let's talk about certain kinds of gear trains. Okay, so gear trains. The simplest kind of a gear train is unsurprisingly called a simple gear train. So a simple gear train basically has more than two gears connected together. So let's say I have one gear here, I have another gear here, and then I have another gear here, okay? And maybe I have another one, okay? And essentially what I'm thinking is, at least without doing any analysis, I want to have maybe a larger speed ratio by employing more than one gear, okay? So this is gear 1, gear 2, gear 3, and gear 4. And I also know a number of teeth on each of those, N1, N2, N3, and 4. And of course, these gears are supposed to properly mesh with one another. So we are saying that their diametral pitch or module should be same, which means that N over D or D over N should be same for all the gears. Okay, so let's say this is rotating with omega 1, then this would be rotating omega 2, this would be going other way, omega 3, and this would be going omega 4 that way, okay? Now let's do analysis for considering two gears that are meshing with each other pairwise, okay? So between 1 and 2, what do we have? We have omega 2 over omega 1 equal to N1 over N2, right? Between 2 and 3, we have omega 3 divided by omega 2 equal to N2 over N3. Okay, between 3 and 4, we have omega 4 divided by 3 equal to N3 over N4. Okay, so I got three equations from three pairs of gears. Let me multiply all of them and see what I get. Okay, so I get W2 omega 2 over omega 1 times omega 3 divided by omega 2 times omega 4 divided by omega 3 equal to N1 over N2 times N2 over N3 times N3 over N4. And this cancels, we get N1 over N4, okay? And omega 3 cancel, omega 2 cancel, we get omega 4 divided by omega 1 equal to N1 over N4, okay? That's the relationship we get. So what does this tell us? This tells us that the ratio between the angular speed of fourth gear and the first gear is only dependent on the teeth ratio on the 1 and 4. There is no teeth ratio N2 and N3 in this formula. So that is almost saying that it doesn't really matter what the sizes of the intermediate gears are. So if this is your input and this is your output, then these two gears over here really don't matter when it comes to finding out what the speed ratio or even the torque ratio would be. Okay, all they are doing is basically possibly changing the direction of rotation. So let's say you want to go from clockwise to clockwise direction rotation. Okay, because if you employ just two gears, you go from clockwise to counterclockwise, right? This is clockwise, this is counterclockwise. But if you employ three gears, then you can go from clockwise to counterclockwise to clockwise. So if this is your input and that's your output, then both your input and output are rotating in the same direction. So this one, it would be called an idler gear. It's called an idler gear because it doesn't really change the speed ratio. So in that sense, both of these two gears, 2 and 3, are idler gears. Okay, these are examples of a simple gear train. Now, where would something like this be, employed? Let's say here was your input shaft and here was your output shaft, and you were really trying to transmit the motion from this input shaft to this output shaft, and they were separated by a certain distance, and you had the gears to squeeze in between. Then you could employ something like this. But of course, this would not be a good solution for very large distance transmission of the motion. Okay, if this distance from input to output shaft was very large, then employing large number of gears would be a bad idea, because at every stage there will be some loss in power because you don't have 100% efficiency. Okay, in that case you are better off actually just employing a single maybe a pulley and cable kind of system from input to the output, something like this, right? So this is an example of a simple gear train. Now if you truly want to get larger speed ratio, you have to use what we call compound gear train. Okay, and the 2 DC motors that you guys have in your mechatronics kit actually do employ compound gear trains. So at the end of the course, if you don't have a use for those motors, by all means try to open them up and see what kind of gear train exists inside them. So the compound gear train, basically the idea is that you have one input. Okay, you have one input, let's say over here, that's your input, and then you have an output gear which meshes with it. Okay, and on the same shaft, so let me draw this like this. So on the same shaft, you have on the same shaft, you have another gear. Let me draw this in a different color. You have another gear. All right, you have another gear like this, okay, on the same shaft. So let's say this is rotating with angular speed omega 1, this is with omega 2, and then both the gear 2, let me label them. This is 1, this is 2, this is 3, both 2 and 3 on the same shaft. So they will be rotating with the same angular speed, but for now let's call this omega 3. And then I have my fourth gear that is meshing with gear number 3. Okay, and this is gear number 4. So this is my input, the gear number 1, and this is my output, the gear number 4. Okay, and we also know the teeth, number of teeth on each of these gears. So this is going in the other direction, that's omega 4. So now let's write the equations. So between 1 and 2, I have omega 2 divided by omega 1 equal to n1 over n2, and omega 2 is equal to omega 3 because they're on the same shaft, and omega 4 over omega 3 is equal to n3 over n4. Okay, so now let's multiply all of these together and see what we get. We get omega 2 divided by omega 1 times omega 4 divided by omega 3 equal to n1 over n2 times n3 over n4. Notice that I didn't have to really bring in equation number 2 here because, you know, that's equality. So omega 2 is cancels with omega 3 because of this. Okay, so what do we get? We get omega 4 divided by omega 1 equal to n1 over n2 times n3 over n4. Okay, so n1 over n2. Now what's n1 over n2? n1 over n2 is the teeth ratio between gear 1 and 2, right? So n1 over n2, clearly since gear 1 is smaller than gear 2, this would be, you know, less than 1, right? So let's say this is a factor of 1 over 10. Okay, and then between n3 and n4, let's say this is a similar factor, and that's 1 over 10. Okay, so what do we get? We get 1 over 10 times 1 over 10. That's just an example. We get omega 4 over omega 1 is equal to 1 over 100. So that's the gear ratio. So in a sense, what you're saying is that by employing a two-stage, this is a two-stage compound gear train, okay, you have reduced your speed by a factor of 100. Okay, so that means that, you know, if your motor was rotating at a speed of, I don't know, 10,000 RPM, your output is now going to be rotating at only 100 RPM, right? So 10,000 divided by 100 is 100 RPM. Now 100 RPM is pretty reasonable. So you're losing on the speed, but what are you gaining on? You're gaining on the torque, right? Because the torque ratio is exactly same. So the torque ratio is same as, you know, as written over here, and that means that your output torque T4 divided by T1 would be actually 100. And this is very useful for robotics applications because in robotics you usually have a large need for torque rather than for the speed. And that's why the DC gearhead motors come with two-stage compound gear train that reduce the RPM of simple toy DC motors by almost a factor of 100. Okay, so simple DC toy motors, and you can go and look them up online to see what kind of a speed they have. Okay, so, you know, let's do a simple, you know, Google search over here for DC toy motors. See what we get. Okay, so simple DC toy motor, something like this, $1.95 at a fruit. Let's see, you know, what their RPM is. Okay, so if you go down here, okay, no load speed is close to 9,100 RPM. Okay, so that's almost like 10,000 RPM. Okay, now this is a very high RPM, and, you know, the torque that you get out of it, 20 grams centimeter, is actually very, very small. You know, no robotics application could probably use this kind of motor unless it was just for some sort of you know, cosmetic purposes. But on the other hand, if you do a search for DC gearhead motors, so DC gearhead motor, and there are different voltage motors, but we'll just do a, you know, simple search for a DC gearhead motor. There's something at Robot Shop. Okay, and, you know, there are quite a few. Okay, let's look at this one, GM9, and I'm just picking something arbitrarily, and this is $5.75. Okay, all right, let's look at the RPM here. Okay, so the no load RPM is 78, so that's close to 100 RPM, right? So you see 10,000 RPM motor has been reduced to a 100 RPM motor, and that has been done by employing actually a two-stage compound gear train. So this part you see over here, this is actually your regular toy DC motor that you saw that was much smaller. This whole rectangular section that you see, if you ever open it up, you will find a two-stage compound gear train inside it. That's basically changing the speed. It's reducing the speed by almost a factor of 100 so that you can have 100 times torque that you would need for high torque applications. Okay.